R.A. Miller Industries, or RAMI, is a manufacturer of commercial and military antennas. The assembly process for one of their most successful products, the blade antenna, has a notably low time efficiency of about 50%. The purpose of this project was to explore possible systems that may be employed to increase the efficiency of this process. The open nature of this project allowed for a variety of solutions to be explored. To fully understand the problem, watch as an operator assembles a blade antenna. First, 2 rivets are gathered and placed in the press. Now, the first half assembly is gathered from the rack, starting at the bottom, working to the middle, longest to shortest. Once the blades are gathered, they are positioned on top of the rivets in the press. A connector is placed on top of the first half assembly. Now, the second half assembly is collected from the top of the rack to the middle, once again longest to shortest. This half assembly is positioned on top of the connector, sandwiching the connector between the 2 half assemblies. The press is activated to fasten all the parts together. Now, the blades must be counted to ensure that it was built correctly. It was determined that RAMI's current assembly process has 2 main areas of potential improvement. First, the long setup and changeover times. A rack fixture must be stocked with necessary blades at the start of a run and emptied at the end. Additionally, the operator must keep their own rack stocked with blades throughout the shift. The high variability of the blade antenna exacerbates this problem. The second possible improvement involves blade handling. The blades are 5,000 thick stainless steel sheets and are very difficult to handle. Blade handling solutions were investigated that could either assist the operator or automate the process altogether. This project has few rigid constraints. RAMI is looking for a solution that will fit into the footprint of their current assembly area for the blade antenna. However, the size constraint is flexible if justification for a larger machine could be provided. As previously mentioned, RAMI wants a solution to accommodate all of their current blade recipes, accepting blades ranging from 2 inches to 40 inches long. To solve the problem, 2 primary solutions were explored. Due to COVID-19, the original plan to design and build an augmented picking system was altered to instead provide RAMI with a bill of materials and assembly instructions as well as the necessary PLC logic for the system. With this information, RAMI could construct the augmented pick system on a later date. Additionally, a prototype of an automated blade singulator was to be made. This device was to be simple enough that it could be fabricated using the limited resources available during the stay-at-home order. The singulator was made to prove that blades could be reliably handled autonomously.
Much of the first senior project semester was spent on developing design concepts and evaluating them. Design concepts were generated based on 4 functionality objectives of reduction, preparation, and changeover time, indication of the correct blade length to the operator, presentation of single blades to the operator, and presentation of completed half assembly. Each design was first evaluated on its operating concept, then a rough cost analysis before the detailed design was completed and then presented to the sponsor. 4 main design concepts were generated and were evaluated on the functionality objectives, restocking improvement, blade assembly improvement, estimated return on investment, estimated production efficiency, concept cost, and concept feasibility. A return on investment calculation was done based on the 2 most popular antenna models and their production volumes. The return on investment calculation estimated the 1-year cost savings of the design concepts and the estimated improvement over current production efficiency. The first concept was the bin carousel concept. This involved rotating the bin containing the correct antenna blade in the assembly sequence to the top of the carousel. The pros for this concept were restocking improvement and the operator having to pick from a singular location. The cons of this concept were no blade singulation, no assembly time improvement, high maintenance, low efficiency improvement, and requiring complex control and high cost. The second concept was a blade pick-and-place system. This involved moving antenna blade bins to an actuated arm that would pick up the blades with a suction tool and then place them on an actuated outfeed table. The pros of this concept were delivering the blade half assembly, allowing the operator to be free while the blades were being gathered, less blade restocking, less blade handling, but the cons were the high cost, more complex PLC controls, maintenance, and the blades needing to be aligned in the stack bins. The third concept was a blade singulation system. which would separate a single blade from a stack of blades using a spinning wheel. The pros of this concept is that no blades would be sticking together, there's a high efficiency improvement, and there's a restocking improvement. The main cons of this concept are repeatability issues and needing a singulation mechanism for each blade bin. The fourth concept was an augmented picking system, which would include short and long blade bins for the different antenna lengths. The operator would be indicated which blade bin to pick from by a light indicator. A sensor would detect when the operator has picked from a blade bin and then know to indicate the next blade bin to the operator. The pros of this concept is that it eliminates setup time, there's no change-up time, and is a high feasibility solution. The cons of this concept is that it will not likely improve assembly time, and there's no blade separation. The augmented picking system and a blade singulation device prototype were ultimately selected to be the focus of the project and to move on to the final design phase.
The augmented pick system is designed to assist operators with the assembly of blade antennas and to reduce the time required to switch over the manufacturing process between antenna models. The system is a rack that can hold 3 long blade bins and 8 short blade bins that are augmented with indicator lights and sensors controlled by a PLC housed in the main electrical enclosure at the rear of the machine. The bottom short bins use PIC2 lights with embedded fixed field infrared beam sensors. The top long bins use LED strip lights and a separate part verification sensor array. The operator interacts with the machine through a touchscreen HMI display and 2 push buttons on an operator control panel. The system is constructed primarily out of aluminum extrusion and is therefore easily modifiable and configurable. The system is designed as a tabletop unit, and the bins have been positioned to keep all of the blades within the maximum recommended ergonomic reach distance. 2 forklift pockets are located on the bottom of the machine to allow for it to be easily transported, even when fully loaded. The bins on the machine are interchangeable and can be swapped out in order to allow for the system to accommodate Ramy's full blade antenna product line. The system can hold more blade lengths than are required for any single antenna model, and many of the blade lengths are common between antenna models. This reduces the number of bins that need to be swapped out during model changeovers. The operator is guided through the bin swap process by the HMI display screen on the operator control panel, which displays a diagram indicating which blade lengths are loaded onto each location on the machine. The reduction in the number of bin swaps and the increase in operator guidance during the changeover process helps to improve the efficiency of model changeovers and therefore reduce the process changeover time. The system works by indicating the next blade in the assembly sequence with a green light and using sensors to determine when a blade has been picked up by the operator. This allows the system to guide the operator through the antenna build process and to detect if an antenna is being assembled incorrectly, reducing the amount of waste and rework due to operator error. It also reduces the amount of training required for new operators to begin creating blade antenna assemblies. Operators simply select the antenna model which they would like to build from a list on the HMI screen, and the machine will guide them through the setup and build process. The system can also be easily upgraded to include new blade antenna models by adding new blade lengths and new antenna recipes to the PLC program. This is important due to new models of blade antennas frequently being created by Ramy to meet custom orders and the high mix, low volume nature of their product. This design was selected from the evaluated designs as the solution to be fully implemented due to its ability to improve the efficiency of the model changeover time, ability to accommodate all of Ramy's current antenna models, expandability for future antenna models, simplicity, reliability, cost, and ease of implementation. These characteristics allow for the augmented pick system to meet the project specifications.
Construction of the fixtures used in the current blade process dates back to over a decade ago. The PVC pipes serve as a tray to house the blades for the operator to grab, then place in the press to complete the assembly. The problem is inconsistent cycle times depending on the experience of the operator. The objective of the simulator prototype was to prove that a single blade could be ejected using a cost-effective design with minimal PLC control. With the augmented picking pin being PLC controlled, the simulator was intended to be an additional design that could be integrated into the augmented picking pin with some improvements for safety and repeatability. The simulator started out as a 3D printed PLA prototype for us to prove out the concept. It evolved to a stainless steel and aluminum construction to increase the strength and resistance to wear, also to increase the rigidity. A stainless steel base was used and landing because they are in contact the most with the blades. The blades are made out of roll-formed stainless steel, so as they're ejecting, there will be a lot of rubbing against the blades in the machine. A 38 durometer polyurethane wheel was used to increase the frictional force between the wheel and the blades while they're ejecting. It actually helps to propel the blades. A stainless steel base was used to increase the rigidity as well and to minimize vibrations. The slot door, see there, it's made out of tool steel because of the amount of rubbing action that happens between the blades and the door when they are ejecting. A harder material such as tool steel will resist wear because the stainless steel is softer. With some optimization via tinkering, the singulation device was performed as expected, ejecting a single blade at a safe speed and having the next blade ready for the operator to grab. In a full design, a proximity sensor would be located at the end of the landing. What that does is that turns off the motor as the blade reaches the end. When the operator then grabs the blade off of the edge, the next blade will come out to eject. Complications in producing the prototype included restricted visitor access in Ramey's facility. As an intern, I was able to fabricate it through our tool room. However, the assembly, testing, and optimization was almost completely done virtually.
The major challenges that were encountered throughout this project include narrowing down the open-ended scope of the project, as well as the abundance of product variety. The project's large solution space, as well as the large variety of product size, were conquered by completing numerous detailed design changes that resulted in the best possible solution for the customer. Due to the worldwide pandemic of COVID-19, we also had to overcome logistical challenges throughout the build phase of the project. By working remotely and shipping materials amongst team members, we were able to overcome the logistical issues and successfully assemble a working prototype for the Blade Singulator.